Welcome back everyone. Now we are going to learn about the Einstein's formulation for the photoelectric effect. Yes, you heard me right. Einstein's formulation for the photoelectric effect. So I am not mistaking anything. So Einstein actually did the mathematical work for photoelectric effect, and in 1905, let me tell you the entire story behind that. In 1905, Albert Einstein published his world-class paper, in which one of the paper is the most famous paper, which is known as Special Theory of Relativity. But do you know that for photoelectric effects formulation, means the formula that we are going to learn now, brought Albert Einstein Nobel Prize, and not his other works like general relativity and all the such things about the gravity and Brownian motion. Nothing, just photoelectric effects study, and finally coming to the conclusion of the mathematical part of it that is lacked in all the observation. We have not studied any kind of the mathematics in that. That is done by Albert Einstein, and that made him world famous in the world of Nobel Prize. So let's study the Nobel Prize work that must be precious. So the story remains pretty much the same. The nucleus is there, the electron is there, and when you put so much or a definite frequency of the light, electron will jump. It should be more than this. So electron starts jumping out and it comes here, as you can see. So it seems quite simple, and we have learned it several times right now, right? So there's nothing tough that gets in here. So what Albert Einstein did in this? Well, he said that E of final minus E of initial gives us the kinetic energy. So how did he came for this conclusion? So this conclusion of Albert Einstein came from a very simple observation that if you give higher energy than the required energy, the electron will come out with some motion, and it is having mass and it will come out with some velocity. So mass of electron with some velocity gives us the chance to get the momentum, but momentum is not equal to the energy or in the difference of energy. So he used kinetic energy, which is half mv square. So on formulation we get something like this: final frequency minus initial frequency. I took the h common here, which is Planck's constant, and kinetic energy is half m, which is mass of electron, v square. So if kinetic energy is 0, so that will be the threshold frequency itself, as you can see in the observation. So this hafty, nafty, safty, well, these are not the words. So these thing brought him the Nobel Prize, and this will going to give us a glimpse that how a simple observation by using mathematics can solve so much of the controversy. You might be pondering that E is seemingly similar, but E is equal to h nu is discovered by Max Planck, and kinetic energy, as we usually know, it was came from the classical physics. So it's just a connection, is it? Well, in some way, yes, because it's just the observation of the experiment that is done by Leonard and Halls and our Hertz and so many people in between and behind. But the most important and interesting thing here is that from this equation, Einstein proved mathematically the observation that is done by so many people that light or radiation is having dual nature, because Planck's formula E is equal to h nu, or also written as sometimes hc by lambda, is actually showing the wave nature of radiation or photons. and half mv square. When you're considering the mass, it is showing the mass. So photon is affecting the mass of electron. It means it is interacting, which means it's particle in nature. So wave particle duality. So he proved wave particle duality with such a great smartness, and that's why we appreciate him and congratulate him. So congrats, Mr. Einstein, you are genius. So take the credit for all those things. But someone is watching everything that Einstein did and took this thing to the next level. To know who he is, stay with me. Take care. God bless.